transform the graph of y equals the absolute value of x to make it into the graph of y equals minus 2 times the absolute value of x minus 4. And we are provided here with the graph of the parent function, the absolute value of x. So that's where we're going to begin. We're going to begin by noting that our parent function, or the basic graph, is that of the absolute value of x. So we can say y is equal to f of x is equal to the absolute value of x. Now, we want to take this parent function and build this up to the goal, which is y equals negative 2 times the absolute value of x minus 4. So let's really apply our definitions here. So I'm going to read these transformations from left to right. So the first thing I'm noticing is that we have y is equal to minus f of x, which is producing minus the absolute value of x. So recall here that if you have a negative on the outside of the function, this is implying a reflection across the x-axis. So we want to reflect the absolute value across the x-axis. So that is our first transformation. Again, reading the transformations from left to right, the next thing that we're observing is that we have y is equal to minus 2 times the original function. Or we can rewrite this as negative 2 times the absolute value of x. So we want to recall here that if you are multiplying your function by a constant that is greater than 1, this implies that we have a vertical stretch by a factor of 2. And let's even be more careful here. Let's say that since the absolute value of 2, which equals 2, since this is greater than 1, we know by definition that this implies the graph is being vertically stretched by a factor of 2. So this means if we're being vertically stretched by a factor of 2, the y values are growing twice as fast. So our graph of the new function is going to be a little bit more narrow, or 2 times as narrow as the original function. And we have one more transformation to go. Again, reading those original transformations from left to right, the last thing that we're observing here is that we have negative 2 times f of x minus 4, which produces the desired function negative 2 times the absolute value of x minus 4. And now we think to ourselves, if we're subtracting a constant from x, what does this imply? Well, keep in mind here that since we're subtracting from x, we can think about this like an x-intercept. So if we have x minus 4 is equal to 0, and we were to solve for x here, so if we add 4 to both sides of this equation, right, the 4's cancel each other out, and we can see that x is equal to 4. So what this is implying is that we have a horizontal shift to the right 4 units. So a horizontal shift right 4 units. All right, so we have everything that we need. We know that our graph is being reflected across the x-axis. The graph is then going to be vertically stretched by a factor of 2. And then last but not least, we have a horizontal shift to the right 4 units. So now at this point, we are ready to go ahead and sketch the graph. But before we even sketch this graph, let's actually plot a couple of points here to really make our sketch as accurate as possible. So again, we'll keep in mind with this last transformation, with our horizontal shift right 4 units, we know that this graph will have a vertex or a turning point at the ordered pair 4, 0. And we know this because we've had no vertical shifts. So let's plot a couple of ordered pairs, or create a table of value and plot a couple of points around where x is 4. So we'll plot 3, 4, and let's do 5. And we know that our y is the desired function, -2 times the absolute value of x minus 4. So when x is 3, we'll have -2 multiplied by the absolute value of 3 minus 4. So that's -2 times the absolute value of -1, which gives us -2 times +1, which is -2. So this is letting us know that we have one solution point on our graph, or one ordered pair, x, y, that is defined as 3, -2. Now, to confirm that our vertex is at 4, 0, let's evaluate at 4. So we have -2 multiplied by 4 minus 4. So we have -2 times the absolute value of 0, which is equivalent to -2 times 0, which is 0. Woohoo! So we have another solution point defined by the ordered pair 4, 0. And last but not least, when x is 5, we have -2 multiplied by the absolute value of 5 minus 4. So this is going to be equal to -2 times the absolute value of 1, which is -2 times 1, which leaves us with -2. And so we can see the balance in the y values around the vertex. So let's go ahead now and sketch ourselves a graph of this transformed function. So here we go. We have our y-axis, and we have the x-axis. And we'll label our scales. So we can say this is 1, 2, 3, 4, 5, 6, 7. So if you have graphing paper, of course, it will be easier to use that. Otherwise, we'll just want to be sure that we label. So 1, 2, 3, 4, 5, so that's -6. Beautiful! So we can plot these points. So we have a vertex at the ordered pair, 4, 0. We also know that we have the ordered pair 3, -2, so right about there, 3, -2. And then last but not least, we have the ordered pair 5, -2. Now the shape of this graph has not changed, so we can simply connect these points with a smooth curve or a straight line to see the graph of this absolute value function. And so there we have it. Here is the graph. Y is equal to -2 times the absolute value of x minus 4.